Hi everybody, I'm Dave Murphy. I'm a professor at St. Lawrence University. I'm one of Charlie Hall's former graduate students actually. So I was at the first ever Biophysical-Economics meeting and for like 4 years thereafter, and then I think I took a break for 1 or 2, but now I'm back. And I want to thank Jessica for squeezing me in. My schedule changed around. I was originally supposed to talk tomorrow, but she allowed me to speak today because this is all I have. If anybody has questions, I have to leave in like a few hours. So if I'm not here available at the end, I'll leave some business cards with Jessica in the back. Feel free to get in touch with me about any of this. And I just want to put a disclaimer, given the last presentation, if that was like college, get ready for basically like nursery level math in my presentation. This will be the complete opposite of what you just saw in many ways. So maybe that's welcome, maybe not, I don't know. But this is work that I've started this past semester with a few students I'm really excited about, but it is very preliminary, and it's not really at a point where I can publish anything from it, and the analysis is, frankly, it's not complete. I'll show you what I have so far, and I'd love to hear any thoughts you have on directions we can go with this. And the title is tentatively Biophysical Boundary Conditions for Socioeconomic Stability. I have a quote to start off. Okay, the quote says, "Blank is a monument of prosperity in blank, with a maze of superhighways and monstrous traffic snarls, skyscrapers and vast housing developments, elegant suburbs, shopping centers, and country clubs, an army of construction cranes, and above all, opportunity." I bet you nobody here would guess that that was a description of Caracas in Venezuela in Latin America in 1974.
And I was thinking it was Aurora.
or Canton, where I'm from, probably. Yeah, exactly. And you know, from this past year, the title is "In the Colombia border town, desperate Venezuelans sell hair to survive." Right. So how does that happen? Right, 40 years, you have such a drastic change and collapse in society. And the reality is, it's complex. Right. It's super complex. You can't often see event A cause event B, cause event C, cause crisis, right? This situation is very, very unlikely to occur. And this is what Joseph Tainer wrote about, right? Collapse of complex societies. And he tried to distill that down and did a really good job with it. But the reality is, trying to predict when crises occur is complex. This is the interpretation of the 2007-2008 crisis in world trade, according to a couple academics published in Nature. I'm not even going to pretend to understand what that math means, but to me it's like dots connect to each other, and then you connect all of these things together. And it just looks a lot more complex than the situation on the left, right? This is somebody's interpretation of how to predict a crisis in world trade. The point, again, being that it is super, super complex to predict when in time and place these crises will occur. So it leads me to like kind of the conclusion here that predicting exactly when crises in socioeconomic systems will occur is fraught with difficulty, largely because the approximate causal variables can be nonlinear and stochastic, right? Just completely random. You can think of climatological events and hurricanes hitting, right? It's really difficult to predict on an annual basis which island will be hit with a hurricane of which strength, right? Of what strength. So it's really, really hard to predict crisis is the point I'm making. So that leads me to start thinking about this from the opposite side, right? So instead of trying to predict crisis, why don't we start thinking about the boundary conditions within which society can exist? So what is required for a society to remain stable, right? What fundamental biophysical variables are required for a stable society? And reducing this down to the very basics, right, you need 3 things. You need food, water, and in modern society, you need energy, right? Because we can't distribute the water or the food without the energy that goes along with it, right? So these were the 3 things that are required for stability in modern society. And the question then was like, okay, well, how much does each society need? How are we going to measure this? And that's when I started going back to ecological literature. Obviously, the idea of stability is inherently tied to the idea of resilience. I started reading a lot of Holling's work and mashing that together with Tainter in my brain. And these are the definitions of resilience: measure of a system's vulnerability to unexpected or unpredictable shock. Adaptive capacity is the ability of a system to regulate resilience, which is kind of like defining itself with its word, which didn't help me much. So I kind of reinterpreted this as saying, adaptive capacity is basically like how large of a disturbance can a socioeconomic system withstand, right, without changing its fundamental properties. And then I started thinking about this idea of like food, energy, water. How much would a society need to like be resilient? How would you measure the adaptive capacity of a society, right? And that led me to this idea of surplus. And this is where like my nursery level math comes in. So let's say we have two countries, right? Country A, country B. Country A consumes, so we have consumption, production, and then surplus. Let's look at year 1, year 2, year 3. And let's say that this is a growing society, right? And country A is producing 10 units and consuming 10 units, but that means there's zero surplus, right? Consume what you produce. Year 1, it grows in year 2, production grows as well. Year 3, it grows and production grows, so everything is fine. Until a disturbance occurs, right? And we could see that. Let's say a drought hits in year 4. All of a sudden, production goes down, and that society no longer can produce enough food to feed its citizenry, right? So surplus is really, really important for being able to withstand these disturbances. The country B on the bottom here is different. Like country B produces more than it consumes, so it creates a surplus in its stockpiles that stores that surplus from year to year. So when that same drought hits country B, they're able to withstand that without changing major function, without collapse, or without major crisis, because they have this storage of food, right? So it's just a basic example. In my mind, I was like, okay, well, that's the adaptive capacity of that society, right? Is the amount of surplus food that it has. So then I started thinking about food, energy, and water again, and thinking about like how this is related to adaptive capacity and societal stability, and it came to the realization that it's not a society that can produce enough food, water, and energy that is stable. It's a society that produces surpluses in all of those that is really stable. And that's, I think, when I started to like plot these things out a little bit. So we can look at this a different way here. So the y-axis is energy, right? Above in the horizontal axis is food. To the right side, obviously, is food surplus. To the left side is a food deficit, okay? Energy surplus on the top, energy deficit on the bottom. So the origin of this graph, right, would be the point at which a society, that would be a country that produces exactly as much food and energy that it consumes. But the problem with that from a resiliency or stability standpoint is that there's zero adaptive capacity. They're producing just as much as they need, and they won't be able to withstand any sort of disturbance to either of those systems. So if we think about it, right, this is the area on the graph that's stable, right? We want to be in the top right of this quadrant, of these quadrants, right? Quadrant 1, I think that's called. These other two are, they're supposed to be yellow, but it doesn't really show up there as well. The top, can you see it out there? No? Okay, well, they're very yellow on my screen. What's the top left quadrant? Quadrant 2? And then quadrant 4 here in the bottom right, those are quasi-stable states. I think I put the words up. There we go. Quasi-stable states, because they have surpluses in one category, but deficits in the other, right? And then in the bottom left is obviously the worst situation, because this is a situation in which a country or society has deficits in both energy and food, according to this. And we can make this three-dimensional and think about water and just do it this way, right? Where you get a green, it's supposed to be green in the top right, so that would be, you have the same idea, right? Surpluses in food, energy, and water, and you're now just doing it three-dimensionally, and you can think of multiple different quasi-stable states in which there's, a deficit in one category and surpluses in two others, right? So this leads to the hypothesis, right? So the hypothesis of all this kind of like background research was that countries with larger adaptive capacity, that's surpluses in food, energy, and water, will have fewer crises than those without surpluses in food, energy, and water, right? Pretty simple, right? So how do we go about testing this hypothesis? And this is where I'm like kind of in medias res, right? I'm like in the middle of, I'm in the thick of like of like going through this analysis. So in my like elementary mathematical mind, this is how I did it. And I'm happy to like entertain any criticism or any suggestions, or anybody that wants to work on this with me, has more time than me. So here's the math, right? It's pretty simple, as I said. So what I did was I looked at the millennium, just because it's a nice round number. I said I'm gonna compare everything to the year 2000. I'm gonna look at changes since 2000 and changes before 2000. And so I created two variables, production and consumption. And X here is food, energy, and water, right? So I did this for 3 different variables, okay? And I just indexed everything to 2000. So I did this for multiple countries, for multiple years, and indexed everything to 2000 so that in 2000, right, the numbers all read 1, right? And then before, okay, great. You all know that. I'm like, I had to run that through my head a bit. But,
Energy as primary energy production?
so I can tell you about the data. For this analysis, I limited it to the countries that have undergone crises in the past 10 years because I wanted to see if I could see anything that reflected this. So I actually use oil here because this is where OPEC nations, mainly oil exporting nations, and I'll talk a little bit about why I did that. There's more rationale just than these are the countries with crises. They're also, the economies are a little bit more simplified, so it made sense to gather the data. Right, I'm calling it energy, but in this actual data I'm going to show you it's oil. And you'll see it's, for food it's cereal, and for water it's something called renewable energy water availability, and then water withdrawals. So those are the 3 variables. I then calculated the surplus very simply, right? So for that country and for that variable, that country and that year, I just subtracted production minus consumption, right? So you get a positive number if you produce more, and you get a negative number if you consume more. And then adaptive capacity is the sum of those 3, right? So the adaptive capacity of any country is the sum of whether or not there's a surplus or a deficit. Obviously, if there's 3 negative numbers, you get a bigger negative number, and if you have negatives and positives, they kind of weigh out, and you get somewhere in between, right? Yeah.
Production include any imports?
Yeah, okay, so good question. No, for food, some of this was a little data dependent. So food production, it's difficult to get food consumption numbers within a country. The data is production and imports. So actually the food data here is production and minus imports, okay? Because assuming that imports are making up the deficit, right? Okay. So to bring you through like a little idea about this math, right? This is how I do it. This is for an oil depletion, a country that has depleting oil supplies, but consumption is increasing within the country. So population is growing and they're consuming more oil, but the domestic supplies are actually declining, right? You get a situation where the index for oil production is less than 1, 0.5, and the index of consumption is above 1, 1.6, showing an increase since 2000 versus a decrease in 2000. Right? The surplus here would then be negative 1.1, right? Once you subtract the negative surplus is the deficit. And then adaptive capacity would be, and I made up other numbers for, let's say for food, let's say that they have surplus food and the surplus water of 1 each. You would sum those and you get 0.9. So this country has a 0.9 adaptive capacity in this way, right? These are all unitless numbers because they're all been indexed, right? And I'm literally making it all up. But I'm trying to get at this idea of like how you can measure these. And let me show you some of the results here. I have them in this software here. Okay, so I'm going to show you all these things on the top. So we have oil surplus, which is my energy, cereal surplus, which is a broad indicator of all the cereals kind of clumped together in the FAO stat, and then water surplus, and then adaptive capacity, and then I'll show you a plot at the end, which is kind of tough to read but cool to look at. And for each one, it's oil production, consumption, and then surplus. So it's the top minus the middle, right, equals the bottom. And any line, if you really just want to pay attention to something, the oil surplus at the bottom, what you're looking for, that dotted line that goes across is 0. And if the lines go above that, it means that there's a surplus since 2000. If the lines go below that, it means that it's been decreasing since 2000. Right? It's pretty simple. And what do you note about all of these countries? Iran, Libya, Saudi Arabia, Syria, Venezuela, and Yemen, right? All of them have declining surpluses, the way I've defined them at least, in oil production since 2000. Okay? We look at cereals, a little bit more mixed for cereal. Production minus consumption, right? None of them have serious growth, but something happened, maybe the world recession around 2006, 2007. There was large declines. I know in Syria, a lot of that was a major drought that hit Syria in about 2009, which declined production and really increased the imports. You can see that right here in the Syria. That's the drought effect. The water data is not awesome. Those of you that have ever dealt with water, but water supply going down, water withdrawals going steady, or Venezuela going way up. And no, I don't know the reason for that yet. I'm trying to figure that out. But the net effect of that is slight decline as well. So what does that mean? Well, the big result I have so far is that since 1987, the adaptive capacity, the way I've defined it, is declining for all of these countries, right? And that, at least in this preliminary sense, I'm not going to go anywhere near as far as to say like I've confirmed or reject my hypothesis or anything. It's all preliminary work. But what it's indicating is that I am seeing in countries that have had, I mean, let's think about this, right? Iran, you could say, has been quasi-stable. There's certainly been a lot of social issues going on in the country, but they haven't had any issues the same way that Syria and Venezuela and Yemen have, right? But all of these countries, in Libya and Saudi Arabia, you could say all of these countries have had cultural issues in the past few years, if not outright civil wars, right? So I'm at least learning enough in doing this analysis that I want to continue doing it, right? I think it's like I might be on something. I'm hoping that I can expand this a little bit. And then you can actually plot this in this software this way, which is that quadrant plot I showed you earlier. And you can highlight the different countries. I think Yemen is in particular really interesting here, right? Because it's got a scattering, but they're generally in the negative area here on oil surplus. So I'm working on getting like a three-dimensional plot of all the variables together, but I haven't done that yet. So what's the next step in this, right? The rationale, I have to expand the analysis so that I can get countries that I wouldn't think, right? I got to get the other side. You're all probably like, well, what does the USA look like if you line it up there? Well, if you line up the USA, which I can show you, I haven't done in Tableau, I just didn't show it to you. The USA kind of looks flat, but the problem with that is that I'm using oil and not energy broadly, right? It's okay to do that in Saudi Arabia because Saudi Arabia uses 95% oil for everything, right? And same with all of those countries. But if you expand to the United States, you want to look at energy surplus, we got to think about natural gas, coal, oil, and everything, and all the renewables. So at that point, I realized that like a few weeks ago, I was like, oh God, I can't that's a lot. There's hours and hours of data analysis just to get these figures together behind the scene to do all the indices and things like that. But that's the next step, right? Is to really make the energy one the proper energy surplus statistic by looking at all of these variables and summing them all together, so that I could adequately represent these countries. And the United States economy is also much more dynamic, so it was a different, it's more difficult. As are like almost every European nation, or advanced economy, if you will. So that's it. That's all I have. Appreciate any questions or comments from the audience. Thank you.